So we've learned some kind of abstract things about quote-unquote thin spherical lenses, and we turn them into these soulless little icons and put them around principal axes and found the images made by objects. Now what I want to do is actual, useful examples of real-world things that are optical instruments. So this is what we have so far. So our base of knowledge is the thin lens equation with its lateral magnification equation, and then we have the lens maker's equation that would tell you how to actually make a lens with a particular focus. So this is the stuff we have at our disposal. And now what we want to do is see how successful we are at describing actual things. So what are optical instruments? And we'll do this in two chunks because one set of these things are simple. It just involves one lens, and another set of these things are compound. So they have multiple images, multiple lenses working together in conjunction, like a microscope or a telescope. So if I think about optical instruments, first thing that might come to mind is a camera, the eyeball, a magnifying glass. And these are all simple, like one lens, one lens, one lens. And then I can start doing exotic things like telescopes, which to understand, you'd need to understand magnifying glasses a little bit, and then microscopes. And we'll basically split things up here and here, because we haven't talked about how the images from one lens might interact with the second lens. So what is a camera? Well, so here's a nice image of a camera. Cartoon, of course. And the job of a camera is to take an object, in this case, I guess, a pretty flower, and it's got a lens, and then it puts it either on the film or in, kind of over the last 20, 30 years, charged coupled device or a CCD. But one way or another, there's a thing called the imaging plane, which, if you're a hipster, is film. For everybody else, is a charged coupled device, or CCD. So this is the lens, and the lens has a fixed focal length. And this would be, hopefully, DI, right? So if you're doing a good job with your camera, what you're doing is you have an in-focus image over here, and you have DO, the object distance, over here. All right, so just put this in a housing and you have a camera, right? And so the job of the camera in some sense is you get to control one of these lengths to put whatever it is in focus. Okay, this is, believe it or not, this is like too pretty. So we've got to turn it into our set of icons. So we have an object, a lens, and an image. So the lens is already basically cartoonified, but this would be a converging lens, as it turns out. And then I'll put a principal axis on here. Instead of a pretty flower, we have a soulless upright arrow. And that is D0, and then DI would be here. So the first thing, if you've solved at this point a couple of problems with converging lenses, what do you know about the image that shows up on the film or the CCD? So I got a converging lens, and this is probably much farther away than the focal length, so we haven't put that on yet. I'll do so now. So we'll say that this is F, and F would be on this side, right? So the light makes it through parallel and would go through this focus. So probably what's going to be true, and turns out you're right if you think this, is that the image is going to be inverted, right? And so what you want to do is, I'll just put this on, ruin our beautiful abstract picture. But what should be true is that this thing should show up in focus on the imaging plane, so where the film or the CCD is. Okay, so in the briefest terms possible, the goal of a camera is that you get to adjust this distance. You can adjust F, and then, presumably you could tell a model to move closer, farther, but if you're taking a picture of the moon, you don't really get to control D0. This is fixed, this is fixed. This is what you're doing when you're focusing the camera. So especially with like an old camera where you're actually literally, twisting the lens. So a camera in the briefest terms possible can be described as focus fixed. That is to say, it's got a particular lens, not fixed by you, the person who's taking the picture, and then DI is variable. So DI is the thing that you get to change to put the thing in focus. So you change the distance in between the lens and the imaging plane. So that's the lens to imaging plane distance. There's another distance that I should have been more mindful of. Okay, so we'll do a really quick example with some actual numbers. So typically, camera focal lengths are quoted in millimeters. So 120 millimeters would be a pretty reasonable common focal length for a lens. So we'll use that and just ask, how do you focus picture of an object, and we'll just say it's 2 meters away. Okay, so briefly what you might have somebody refer, or talk about is 2 meters away from your camera. I'm going to use really precise language for this. I'm going to say 2 meters away from your camera's lens. Because maybe we don't have enough experience with this to start getting casual, but specifically 2 meters from the camera's lens, if the camera has 120 millimeter focal length. And we'll put a plus on that because it is a converging lens. So a virtual image located back here is not going to do anything at all for your camera. You literally want the light rays to come through and show up in focus on that point. So you could pause and figure this out. Probably wouldn't be too difficult, but I'm going to do the whole shebang with the object and then the camera lens and then the imaging plane. So from here to here, totally not to scale, is 2 meters. And then from here to here is I don't know. But what I want to have happen is I want to have this distance be the distance in between the film or the imaging plane so that this shows up in focus, right? So use the thin lens equation to figure out where DI is, given the fact that we have the object distance in the focus, and then basically, put the lens so close that it shows up at that point, the imaging plane. And you've got a focus that, would be like really close. So, 12 centimeters versus 2 meters, it should be really close. So F would be like there or something. Okay. And as always, if I've got nothing better to do, which I don't, I should draw a ray diagram to see what I should kind of expect for an answer. So I've got my easy ray, parallel focus. I've got my not so easy ray, focus parallel, and then I have my center ray. So it looks like I should get as expected, an inverted real image that's located pretty close to the focal length. Okay, so I'll do this, use the thin lens equation, and that's 1 over 120 plus 1 over 2 equals 1 over 2 plus 1 over DI. And then math happens, and I can hear you cringing through the space-time continuum. So the one thing that you have to do when you solve these optics equations is you don't have to be SI, but you do have to match units. So this is really gross. And there are 2 ways of doing this. I think I'm going to express everything, just meet in the middle and do centimeters. So this 2 meters will be 200 centimeters. And this 120 millimeters will be 12.0 centimeters. So one way or another, got to have not SI units, but consistent units. Okay, and let me just make sure this is positive because it's always positive, the object distance. This is positive because this is a converging lens, everything looks good. Math occurs, and what I end up with is the eye should actually be pretty close to the focus, like 11 point something centimeters. Remember, right? 11.3 centimeters. Okay, fine. This is, so, if you have a nice camera, what you have to do is kind of turn the bayonet lens until the focus is far enough back so that, the distance is 11.3. Okay, you may have noticed that this doesn't happen at all on the thing that you take probably the vast majority of your pictures with, which is to say there's no micromotor that's moving your phone's lens in and out. So there's a rule of thumb, and now you know how your phone actually takes pictures. Let's say that f is really, really small. And what that really means is f is much, much less than the object distance. So I've got a focal length that's this big, and I'm taking pictures of something that's like pretty far away. So effectively what happens to this equation, 1 over f, 1 over d naught, 1 over di. Well, if this is tiny compared to that, effectively this becomes really big. Really big for us is infinity. 1 over infinity is 0. So essentially, if you have a tiny focus lens and you're taking pictures that are far away, you don't really have to do any of that mechanical focusing. I mean, your pictures aren't going to be great, but you don't have to, pay the price of actually literally mechanically manipulating a thing. All you have to do is park the imaging plane essentially at the focus. And you can almost see that here, where even at 2 meters away, we have a focal length of 12 centimeters. We had to move the imaging plane to 11.3 actually. So the rule of thumb, if you're really far away, light at infinity will always focus make an image at the focal distance. That should sound familiar. That was the whole point. So this is actually how your phone works. Okay. So the next optical element that we want to talk about is the eyeball. So essentially focus fixed, object fixed, DI variable. The eyeball is basically like a squishy camera. And this is a way simplified picture. Go ahead and look up weird kind of grody images of eyeballs and diagrams on the internet if you want. But this is a physicist eyeball, which is to say we simplified the living crap out of it. And there's a bundle of optical nerves, and then there's a thing, and then there's a lens, and there's some cute little muscles, and then there's a whole bunch of rods and cones, which is the imaging plane. And what you can do is you can squeeze the lens to change its properties. So essentially you can squish your lens, the lenses in your eyes, to change their radii. So what happens when you squish and change the radii of the lens in your eyeball? You change the focus. So in fact, an eyeball is characterized by the following, is that so your eye doesn't get longer or shorter, so in fact the imaging plane is fixed. So opposite to a camera in some sense. F is variable, and let's say you want to look at something and you can't encourage it to move, this would be essentially fixed. Okay. And as a rule of thumb for most of us, what this is about 24 millimeters or 2.4 centimeters. So that's the typical eyeball length from the focus, the lens, to the back, the retina. Okay. So likewise, we could draw some diagrams. I think this is actually much more interesting, is we could take a little bit of a detour into optometry school, because there's a limit to this. So there's a limit basically to the ability of the muscles in the eye and the lens to kind of mechanically squish or contract them. And you basically don't get, a full range of foci. And instead of worrying about the details, the kind of biological details of the focus itself, because you could imagine maybe the lens maker's equation is, isn't precise enough to talk about this. All we want to do is we want to talk about effectively how good you're able to focus by establishing what's called a near point and a far point. So the idea is that we're just going to characterize how good our eyes are by taking a thing, an object, and just moving it back and forth until we're no longer able to keep track of it and it's no longer in focus. So here, where this thing goes out of focus, this is what we'll denote N and call it the near point. So I'll show you how to find your near point in a second. And then we'll go out here and we'll have a thing called F, which you'll be astonished to learn is called the far point. And that's basically the distance of the farthest thing that you can focus on. Okay, so the whole point of optometry school is essentially to correct the eyeball so that it has a near point and a far point that's good enough. Kind of society seems to indicate that we should have far points that are, infinity, and I think the near point that we'd love you to have is like 40 centimeters or something like that, I think, typically. So ideally the near point would be 0, but in all likelihood it's probably like 25 centimeters. So I don't want to even bother putting units on infinity. Infinity is infinity. Okay, so we usually don't have this. So you can find your own near point by the following experiment. You can just take your finger and then move it closer and closer to your eye until you're just not able to focus on it. That's your near point. I actually have a really good near point. My far point is pretty bad. So likewise, you could find your far point by moving something farther and farther back until you can't focus on it. So this is what, we would love it if you had, but biology has other plans. So how do you correct for this? So you correct for this by putting a lens in front of your eye. What does the lens in front of your eye do? So the lens in front of your eye, and this is like the whole point of corrective optics in general, is the lens in front of your eye creates a virtual image. So we'll call this the big idea in corrective lens wear. I don't know when people came up with this, maybe in like the 16th century. And they definitely didn't talk about it like this. So we'll create a virtual image of some object at N or F. So this is what we want. You'd love to see something that's at the near point or at the far point. You just can't do it. What you have is your own personal crappy near point or far point. So what we're going to do, and the job of the lens is going to create a virtual image of the thing at the actual near point or far point at where your biology can take over. So we want to create a virtual image of the object at your near or far point. Okay, so that actually is like kind of a clumsy way of writing it. It's actually much easier to, diagnose your own vision. And the virtual image thing is really, really, really important. The last thing on earth you want to do is create real images on the back of your retina, because that would be a converging lens. Think frying ants with a magnifying glass, but the back of your eye, like that's not good. So definitely a virtual image. Okay, so this is probably more helpful. So let's say when we were doing this, you found that you couldn't focus on things that were closer than 50 centimeters. So you have a 50 centimeter focal or near point. So we'll say your eyes naturally have that. So I like pictures. So what we have is, I would love to have something that was actually at, so this is my eye. And I'll actually, just so we don't really think about it as a lens, we'll just draw the eye, really gross. So there's my eye, and this thing is at a distance of 25 centimeters, which is what society tells you you should be able to focus on, right? I can't do that, it's too close. So what I want to do instead is I would like to make a virtual image. The other reason you know that corrective lens wearer is making virtual images is because real images tend to be inverted, and you don't want to see the world upside down when you put on your glasses. So the thing's actually here. What I want to do is I want to create a lens that puts it there. Okay? It's as simple as that. And I have object distance, I have image distance. Honestly, technically, what should happen, so here's the lens itself, and this will be like a meniscus lens. You probably should worry a little bit about the distance in between the eyeball itself and the lens, at least for correcting farsightedness if you have a crappy near point. But we won't do that because I'm just showing off what the general idea of corrective lenses are. Okay, so I've got this image, right? So without the lens, you can't see this. With the lens, I create a virtual image here. So let's not worry about the eye anymore. And what I have is a diverging element. It's probably not going to look like that, but now we're in cartoon world. And I have an object that's actually located at 25 centimeters. So that's D naught from there to there. And what I'd like to do is I would like to make a virtual image here. Okay, and I know that my focal length is going to be negative, and I know that DI is also going to be negative because sign convention says same side as the object for a lens means that's negative. So all I have to do is just make sure I know what my signs are and plug this into the mirror equation. So I have 1 over F, that's what I'm looking for. 1 over D naught, that's 25 centimeters. That's where the thing actually is that I'd like to see. And in order to do that, I've got to place a virtual image, so negative, at 50 centimeters. And then math happens, and F is equal to 25 centimeters. Right? Oops, sorry, 50. And negative. Okay. Oops. Do that right? Yeah. Oh, sorry, this is a converging lens. Yeah, my mistake. Yeah, slightly converging. But it's in the regime where it's making a virtual image. Sorry, I misspoke earlier. Yeah, for farsighted people, you can tell I'm not farsighted. You do want a slightly converging lens, but you still don't want it to make a real image. Yeah, so this is definitely positive. That makes sense. Okay, one note about this is that you never actually see focal length of like blah, blah, blah meters. If you look at your glasses prescription, for instance, what you see instead is what's called a power. This is a total cultural note. Because it's not the power that we talk about in mechanics, which is why it's kind of annoying to physicists, is in a unit called diopters. And the power of a lens is basically 1 over the focus, measured in meters. So the power of this lens, and this is what you would actually see on a optometrist prescription, would be 1 over 0.5 meters, putting that in meters, or a 2 diopter lens. So if your near point is actually 50 centimeters, to give yourself the society-approved near point, you would need a 2 diopter power lens. Okay. So the far point thing is pretty great, and I'll just make a comment about it before we move on, is that because ideally your far point should be infinity, when you dump stuff into that equation, you want to make a virtual image at infinity for, so you want to take an actual thing at infinity and dump a virtual image somewhere at your biological far point. So let's say here's your eye, and this will be a diverging lens. So let's say you've got an actual far point of, for instance, 10 meters. Beyond 10 meters, everything is fuzzy. So there's a thing off at infinity, so I'll just like ... So d naught is at infinity. What you want to do is you want to find a virtual image, place a virtual image, again, here, right? And to do that, you'll actually use a diverging lens. So skipping the part with the eye, just ignore that for a second. We've got some focal length. I don't know where it is. This is a diverging lens, so the focus will be here. Want to take an object at infinity, and we want to place it there where our biology can basically just take over. And the nice thing that happens is we get a 1 over infinity. And again, just like cameras focusing on something really far away, the math gets pretty simple. So 1 over f. For this person, for instance, for me, I can't really focus on anything farther than 10 meters. I want to take something at infinity and place a virtual image, so negative, at 10 meters. 1 over infinity is 0. F is minus 10 meters, or the power of the lens, 1 over f, is minus 0.1 diopters. Can you even believe that people go to optometry school for years to do this stuff? Just kidding, they learn about all sorts of important stuff involving like diseases of the eye and astigmatism or whatever, but this is the basic idea. You always want to create a virtual image for far-sighted people that will involve a converging lens. But you always want to create a virtual image at the place where your biology can take over. Okay. So we have one last simple optical element that I at least want to mention a property of before we're able to understand telescopes and microscopes. And that is a magnifying glass. So a magnifying glass, it's kind of weird because in the age of photography, you don't need like this Sherlock Holmes stuff to magnify stuff. Just take a picture and like mechanically enhance it. But the idea is important. So I've got a tiny little thing like a bug or a, blood spatter or some sort of clue. And the magnifying glass works like this. I mean, the way that people use it when you're, kind of watching an old movie is correct. So you hold the thing up really close to what you're trying to magnify and then move your eye in to do whatever it is that it's doing. So the thing that's happening is kind of interesting. And it's something, this is more important than the magnifying glass itself. So I'll take this big thing, and then I put my eyeball there, and then we're going all Sherlock Holmes. So we've got this. And everything's all close together, and this is a big honkin' lens, right? So everybody knows that. So, we've got some fingerprint or whatever. I don't know. So what is it that you're trying to do? What you're trying to do is magnify it, but not lateral magnification. So lateral magnification actually doesn't end up telling the whole story. So really what you want to do is angularly magnify the thing. And you angularly magnify stuff all the time. So here's your eye, and here's an object, which could be like a small word on a page or something like that. And it's too small for you to read, right? So what do? You don't resort to like exotic optical things. You just get closer, right? So I haven't actually changed the height of this. So I haven't done any sort of lateral magnification. I mean, there's no nary a lens involved. But just by virtue of getting closer to the thing, what you've done is, we'll call this theta 1, and you've increased the angle on your eye that it subtends, is the kind of fancy way of saying it. So the more space it takes up on your eye, the finer details you're able to see. So this is angular magnification. So angular magnification, we'll call it big M, is given by the ratio of the angles on which it subtends your eye. And in fact, roughly speaking, this is approximately true. It's technically a tangent. But until you get like really up in your eye, you can express this in terms of the ratio of, so for theta 2, that would be height of the second object divided by the distance of the second object, and the height of the first object divided by the distance of the first object. So, really should be like an arctan in there somewhere, but basically the ratio of the height to the distance, So this is height 2, and this is distance 2. And the bigger the height versus the distance, the bigger this angle will be. Right? So that's angular magnification. And this is actually more important. So angular sizes are, for instance, why the sun and the moon appear to cover each other during an eclipse. It's certainly not the case that the sun and the moon are the same size, but they have the same angular size. They subtend the same amount of space on the sky. So I'll just say this without proof and draw a little picture. So this is kind of important. Let's say that I have one lens. How can I use one lens to do a good job, do better than I can do by angularly magnifying something? And in pictures, the way to do that is I've got a lens. It's going to be, we know it's going to be this big Sherlock Holmes lens because, you know how magnifying glasses work. And I've got a focus. I'm going to put the focus on both sides. So there's, just in case we're worrying about light coming from the left or the right. And I'm going to tuck an object right here, just because. Actually, just inside the focus. So I have an object. I'm going to put it right inside the focal length of this thing. And what you're going to see is that, kind of talked about this a couple of times now, is that I'm going to basically blow up the thin lens equation. So if I have, and this is a way we haven't blown it up yet, if the object is just about located at the focus, what happens to this equation? Do we need any di? No, these are already equal, so we don't need that. Well, how do I make this term disappear? I make this whole n term disappear by basically having the image show up at infinity. So not exactly at the focus, but as we start getting near the focus, we're starting to mess with this 1/0 kind of hyperbola thing, and the image goes off towards infinity. Well, so the thing about the image going off towards infinity is the image gets like really, really big. So I'll draw two rays. Drawing ray diagrams at the focus is challenging, but enough to get the point across. So basically, I have this converging lens. I'll put this about at the focus, pretty close to it, and then I'll start trying to draw, and here's the other focal length. Ray 1 is easy, in parallel out through the focus. Ray 2 is where we start going sideways. So this thing goes straight through. This thing I can't even draw. Ray 2 is really tough. It's basically going to go, from the focus out parallel. Well, that would be like straight up or straight down. But from the two I can draw, what you can see is they're probably not going to converge. They're going to be parallel. And if they do converge, it's going to be like way out here. My goodness, look at how big that image is. So what you do with the magnifying glass is so the story of a camera is that I have a fixed focus and I adjust DI mechanically. The story of an eyeball is I have a fixed DI and I adjust F mechanically. The story of a magnifying glass is if you put the object, so this is the one where you're able to move the object, about at the focal length. what you end up with is a huge DI and therefore HI, and that gives you a large angular magnification. So the actual magnification, if you put the thing right at the focus, would be infinite, but some of these things, so you don't quite make it to infinity. And roughly speaking, if you do that, and you tuck your eyeball at the near point, so what you want to do is be as close to the magnifying glass as you can get and still focus on it. So roughly speaking, the way that they work in practice is you get an angular magnification that's dictated by both your eye, how close you can get to the thing, and the focal length, which is how far away the object can be tucked. So these things kind of cancel out, and you can see that F is DI, and then on the other side of this triangle would be N, the near point, how far you can get to this. So N would be here. So roughly speaking, you get a magnification. All I want to do is say that the point of a magnifying glass is if you tuck the object like dangerously close to the focus, you make the image blow up and it appears larger. So what we'll do is we'll need that to discuss how you get telescopes and microscopes to work.